Today, we're going to take our solving systems of equations one step further, and we're going to learn how to do that algebraically using something called substitution. And substitution is exactly kind of what you think about that if a teacher isn't here, a substitute comes in. That's kind of what we're going to see happening today with our systems. So you're going to remember that the last video and in class, we practiced how to solve a system of equations by graphing and how to check our answers if possible. So I have one up here and I'm just going to remind you of that process and maybe show you why we might need a new method. So I'm going to start with that blue line, and you're going to remember that it is in a form easy to graph in that it's y equals mx plus b. I'm going to get my eye on that b. I'm going to grab a point. I'm going to go to the y-axis to the 4. There is my y-intercept. I'm now going to grab another point, and I'm going to move from that point a slope of -2. So my rise would actually be a fall of 2 and a run of 1. And there I've got my 2 points, and I could do that again, down 2, over 1, and then I'm going to pick up my ruler, draw on the line and arrows, and that would be the line y equals -2x plus 4. Now I'm going to do the same thing with the red line. I'm going to start at the y-intercept, which is a +1 on the y-axis. I'm going to grab another point and I'm going to use the slope +2 over 1. So I'm going to rise 2 and run 1. And I'm going to do that again. I'm going to rise 2 and run 1. And I'm going to draw my line in. And you'll notice when I did the slope, I kind of didn't hit the other line. So there's kind of a question mark as to what is that point where the two met. It's some kind of fractional or decimal value. It's less than 1 for its x, and it's between 2 and 3 for its y. And I don't know what it is because it didn't fall in the crosshairs. So here is an example of a system that graphing isn't going to get us the answer. I am going to tell you what it is. The x value of that point is 3/4, and the y value is 5/2, which would be 2.5. But you're kind of guessing unless we use a different system. And that's what we're going to do today. So the system is called substitution, and we're going to start. I'm going to do one with you, and then I'll let you know where there's an example in the book as well. So you'll kind of get 2 of each here. But basically, when you're solving a system of equations using substitution, there's no graph paper or ruler involved. So basically, I'm going to start with an example where both are y equals mx plus b. They do not have to be, and I will show you one in a second. So they can be set up a little bit differently as well. But let's start with this example. So basically, what I'm noticing is that the y is the same. Y equals x plus 1, but y also equals 3x minus 5. So because they both equal this y, they can both equal each other. It's called the transitive property in math, but if something, x plus 1 equals y, and then that same y equals 3x minus 5, then these two things have to equal each other. So what I'm going to do is I'm going to take that top equation, I'm going to rewrite it, and I'm going to take that y out, and I'm going to substitute the 3x minus 5. It's kind of like if I wasn't in class, if I had to leave, I'm y, and Ms. Marino came in and took my place, and she's 3x minus 5. So the y leaves, and the 3x minus 5 takes its place because y equals 3x minus 5 as well. This is now an equation with a variable on both sides that we did in Unit 3, solving equations. So we have the choice. You remember that. I can either subtract x or I can subtract 3x. And I talked about this as going left or right as you left the door of the room. I'm going to subtract x. That was my choice. And I put it under its like term. So 3x's take away 1x would give me 2x. I did not touch the minus 5, so I write that. Here is the equals, and x minus x is my 0 pair, and 0 plus 1 is 1. And now I'm left with one variable, and we're going to grab a Woodruff bubble here, and we're going to Woodruff bubble this and not touch that variable, that 2 right now. I look outside and I need to move the minus 5 to the opposite side. opposite sides, opposite operations. So that -5, to get it to zero out, I need to add 5 to make a zero pair. And whatever I do to the left, I have to do to the right. So I get 2x plus 0, which is just 2x, equals 1 plus 5, which is 6. Now the opposite of multiplying by 2 is dividing by 2, and I get x equals 3. That is the x-coordinate of where these 2 points intersect. I need the y-coordinate. That's only half of the answer. So now I'm going to take that x equals 3 and I'm going to substitute again. And you kind of have a choice. You go back to either the blue, the top equation, or the red, and you take out the x and you put the 3 in. I'm going to do that on the next slide. So I picked the blue, I took out the x, and I put the 3 in, and 3 plus 1 is 4. So my solution is 3, 4. Those two lines, if I drew them, meet at 3, 4. Well, Mrs. Woodruff, I could have graphed that one because this would be in the crosshairs. And I do realize that. I'm trying to give you examples right now that don't have fractions, just so you can understand the method. So the numbers are going to come out to nice answers right now. Now, I recommend that we check our math. Since I just used the blue equation to get the 4, I really just need to check it in the red one, which was the y equals 3x minus 5. So the x is going to leave and the 3 is going to fall in, and the y is going to leave and the 4 is going to fall in, and we're going to see if the math works. So PEMDAS, we're going to multiply 3 times 3 and get 9, and 9 minus 5 equals 4. So I'm feeling, confident that 3, 4 is the solution to my original system. And let me just remind you, it's right here. So if you graph those two lines, they would meet at the point 3, 4. There is one in your book on page 244, example 1. You notice again, y equals x minus 3, y equals 2x. They are taking out the y in the top and moving that 2x in, substituting, and they do have a variable on both sides. They have the choice right now. They could either subtract 2x or subtract x. They could go left or go right. They subtracted x, and they get right to the x-coordinate. When I go to the next page, you're going to see this again because I just want you to see that we need to now get the y-coordinate. So here's what we just did. To get the y-coordinate, I've got to take one of these x's out and put in -3. So I took out the y right here and took 2 times -3 and got -6, and there is my coordinate point. Now the book has this stupid idea that in order to check it, you should graph it. And that's why Mr. Yuck is here. Nobody would ever do that. We would never graph the system to check the substitution. So that's just a Mr. Yuck. To check it, you just take the other equation that you didn't use. So to get the y-coordinate, I used the y equals 2x, the bottom equation. So I just need to check my answer in the top one. I need to make x be the -3, and I need y to be the -6, and check to see if it works. And if you take -3 minus 3, it does. So just disregard this craziness, will you? Okay, so speaking of the book, on page 244, there are 2 got it, so I'm going to let you have a chance here. So A is pretty simple. The y-coordinate is 2. They've already told you that, but now you have to find the x-coordinate. So you're going to take this equation right here, and you're going to take the y out, and you're going to substitute the 2 in and solve it. So the video is going to pause and let you do that. Come back, and we'll see how you did. So that substitution basically looks like that. The top y left and the 2 took its place. And oh my goodness, this is a one-step equation. We just need to get rid of adding 4. And the opposite of adding 4 to be able to leave that x by itself is to subtract 4. So when I take 2 minus 4 on the left, I'm going to get -2. And I'm going to have that equal x plus a 0 pair, which would just be x. And boom, I'm already at my x-coordinate. So the point is x of a -2, a y of a +2. That's where those 2 lines meet. I need to check that answer in that top equation. So the -2 is going to take the x spot, And the positive 2 is going to take the y spot, and really simple math there to check in the calculator. Okay, how about trying B? So the top y is going to become 3x because y equals 3x, so I can make that substitution, and it's now a variable on both sides. So you can either go left to make your zero pair or go right. I'm going to subtract x from both sides, and I get 3x minus x, which would be 2x on the left. I'm going to get a zero pair, 0 minus 6 on the right, and I end up with, whoops, there's my crazy mouse, 2x equals negative 6. Now I'm going to take and undo multiplying by 2, which is to divide by 2, and I get x equals negative 3. So if I was to graph these two lines, where they intersect, we'll have an x coordinate of negative 3, but where's the y coordinate? So this time they didn't make it so easy. They didn't give it to me. So I have to take that negative 3 and put it in one of the equations, your choice. And I chose to put it in the bottom one because I thought that was a little easier. So I'm going to take 3 times negative 3, and I think the y coordinate is negative 9. So right now, I believe the intersection point, the solution would be negative 3 comma negative 9. I'm going to check it, but I don't really need to check it in the one I just used. So I'm going to just check it in the top one. You can always check it in both, but I'm going to check it in the top one. I'm going to put negative 3 in for x and negative 9 in for y, and sure enough, it works. So now you're going to remember I told you at the beginning that they don't have to both be y equals. So if you look at the example I'm going to do, which again, I've made one up, and then I believe there's one that I'm going to show you from the book. But you need one of the equations solved for one of the variables. So if you'll notice here, the top equation is solved for y, but the bottom one isn't. And you're good to go with substitution as long as that is the case. So this time, I really only have one choice. See the y right here in the second equation? He's going to leave. So if you come down here and look at the second equation, 6x plus 3y equals 3, that's me. I'm going to leave the equation, and Ms. Marino is the 3x minus 9. We are equal. So she's going to take my place. So the y is going to leave, and the 3x minus 9 is going to come in and take the place. Now, we did equations like this in Unit 3, and when we saw the parentheses, we said, oh, that means I have to use the what? What do you have to do when there's parentheses? And you're going to remember that you have to do the distributive property. So you're going to take that 3 and multiply it by the 3x, and you're going to take that 3 and multiply it by the 9. Now, I'm just going to back up for a second just so you can see, that where that kind of came from. So 3x times 3 is 9x, and 3 times 9 is 27 with a minus in between. So distributive property. Everybody in the group gets multiplied by 3. Now, we're tempted to go try to Woodruff bubble, but we can't because there's two terms here. They're on the same side. So we're on the same side. We do same operations. So we're going to just combine like terms. You might remember that from Unit 3. So 6x plus 9, 6 plus 9 gives me 15x's. And now I'm ready to do my Woodruff bubble and not touch that 15 that's in front of the x. So I get my I on the minus 27. To make a zero pair, I got to add 27, and whatever I do to the left, I got to do to the right. So the 15x plus 0 equals 3 plus 27 is 30. Remember, we undo multiplying by dividing, and I got x equals 2. Now I need that other part of the solution. I need the y coordinate, and your easiest bet right now is to go up into that top one and simply take the x out and put the 2 in. If you put it in here, you got too much work to do. So you're going to put it up here where that x is and take 3 times 2 and subtract 9. Pick up my calculator if I need to, check myself, but 6 minus 9 is negative 3, and I believe that's my solution. I'm feeling really unsteady on this one. Wasn't so simple, so I definitely want to check it, and I'm going to check it in that more complicated second equation. Let me just go back and remind you right here, the 6x plus 3y equals 3. I'm going to put the 2 in for the x, and I'm going to put the negative 3 in for the y, and I'm going to see how it goes. So I do my PEMDAS. I multiply 6 times 2, and I multiply 3 times negative 3. And thank goodness, when I add 12 plus negative 9, it works. And that's my solution. So just to show you on page 245, they did one just like this as well. So they have that more complicated equation, and they take that y out and drop in the 3x plus 8. They're showing you very nicely the distributive property. They're combining the like terms. And right here is where we would be, right here rather, where we'd be Woodruff bubbling and subtracting 32, dividing by that 20, and the answer would be negative 1 for the x coordinate. Now go back up in the simpler one and put 3 times negative 1 and add 8, and you'll get the y coordinate. And you'll see them doing that. And they get, whoops, sorry. Where did they get that? Oh, right here, sorry. So they put the negative 1 in, and I don't know why I repeated that. So there's the negative 3 plus 8, which is 5. And there is the solution. And again, don't graph it. Just put it back into the more complicated equation of the 2. X times the negative 1 plus 4 times the 5. Multiply and add, and you can check your solution. Nobody graphs to check them. So here's a chance for you to try. So pause and see if you can do C. So let me just uncover and see how you did. Did you get an x of 2? I'm going to remember you can pause the video to kind of check your math. And then did you take your 2? Did you put it right there and take 2 times 2 plus 1 to get the y? Did you get a y of 5? So your solution point where the two lines would meet is 2, 5. And then to do the check, you need to check it in the second one because you've already used the first one. And did you do a good check? So again, if you need to pause and kind of see if you made an oops somewhere, all the work is there. You can go ahead and check it. Otherwise, the video is going to pause and ask you to try the second one. So give it a go again. So this time the y equals mx plus b equation was on the bottom. So you're going to take this y out and substitute the 6x minus 4 up into that y this time. So that should have been where you started. Distributive property, like terms, Woodruff bubble, and don't touch the 32. Add 20 to both sides. Divide by 32, and your x coordinate of the intersection point would be 2. The 2 is going to take that x spot right there, substitute 6 times 2, take away 4, and your y coordinate is 8. The solution to the system is 2, 8. And then I'm just going to ask you to check it by putting the 2 in for x here, the 8 in for y there, PEMDAS, and there is your check. So the only thing that we have to just kind of mention is what happens in substitution. You can't see the lines being parallel. You can't see them being the same line. So how does that happen? So I just wanted to show you kind of a quick example. And the minute you see it, you're going to remember we had something like this back in Unit 3. So, hey, I know what to do. I'm going to take this y out, and I'm going to drop the 3x plus 1 right in there. I'm going to do my distributive property, and this is a negative 2 times 3x and a negative 2 plus 1. If you can't see that, same change and make that 6x plus a negative 2, and you'll see that you are distributing a negative 2, and you should get that. And notice what happens this time when I have like terms. If I have 6x's and I take away 6x's, that is actually 0. And I'm going to end up with that craziness. And you might remember that happening before. And when that happens, that is called a no solution. Do you remember that from Unit 3? Because negative 2 sure doesn't equal 5. In this case, no solution means that the lines are parallel. We'll talk about that on the next slide. Now, let's do it again. This time I'm going to substitute up. I'm going to take that y out. I'm going to put the 3x plus 3 in its place. I'm going to do my distributive property, get 6x plus 6. Here comes that 0 again, like I saw over here, and I end up with 6 equals 6. This time, we have that infinite number of solutions, and in a system, that means it's the same line. So these are the identical line that if you graph them, they'd graph right on top of each other. So just sort of to remind you and recap that, no solution and infinitely many, you look at that, the variable drops out, and then you kind of look to see, is it true? Like this one, it's infinitely many. And if it's false, it's no solution. So if it's not true, it's no solution and it's infinitely many. So again, no solution is parallel lines, and an infinitely many would be that they're the same line that we saw when we graphed in the last section. So today we're doing substitution, and kind of, I know it might be a little bit, oh no, for some of you, but in a way, this is really good to kind of do a review of solving equations and kind of get those ideas back that we did sort of before our winter break. So you're going to come into class and we'll do some together, and then you'll practice and have a little chance to do some IXL, and you will become a pro at this, I promise. In the meantime, have a great day. I'll see you soon.